just say hello and then basically turn off my video and then come back to you at the end. So, starting with the hydrogen bonding. Let's see if I can have it full screen. Yeah. Hydrogen bonding, is basically water is very strange compound because it can form hydrogen bonding. So, and hydrogen bonding is basically the electron loses, hydrogen loses electron to oxygen. So it becomes partially positive, and the electron cloud of oxygen is partially negative. So in addition to van der Waals forces, you have hydrogen bonding. That gives water very stable condition. That's why water can freeze and can melt or become liquid at relatively high temperature. So when water is in the liquid state, you have this hydrogen bonding and they form shape like this. And if we have gas molecule, this green sphere is the gas molecule. And this red is oxygen, the white are hydrogen. So when we have gas molecule, the water molecule get trapped in the cages that water molecule forms. So the gas molecule become trapped in the cages that water molecule will form. For the formation of hydrate, we need hydrogen bonding. So either we need water or ice. And then we need suitable size molecule. So if the size of the molecule are too big, they cannot fit in this cavity. And therefore they cannot form hydrate. And we need suitable temperature and pressure condition. So suitable temperature and pressure condition is this curve. To the right, we don't have hydrate. To the left, we have hydrate. Now the position of this curve depends on the composition of hydrocarbon phase and composition of water phase. Now, relatively, the position of this water molecule in this structure is fixed. So how much this gas molecule is close to the water molecule depends on the size of gas molecule. If they are very small, the interaction is not very strong. If it is very big, again, they repel each other. So like here, imagine we have a molecule here. If the other molecule is somewhere here, there is no interaction between this molecule and this molecule. So interaction is zero. So if we have a molecule like hydrogen or nitrogen, it's very difficult to form hydrate. But when the molecules get closer to each other, they basically change the polarity, so the electron goes to one side, the proton the other side, and they form the van der Waals forces. So they attract each other. So like here, you see that if they get close to each other, they attract each other. If they get too close to each other, they repel each other. So molecules like isobutane or propane, like cyclohexane, they have high tendency to form hydrate. So you see that this curve is a function of the hydrocarbon phase composition, gas phase composition. The other important factor is the composition of water. If we have components that are dissolved in water, for their dissolution, some water molecules should be around them and make them dissolve. So therefore, less water molecule is available for hydrate formation. And therefore, this will work as a hydrate inhibitor. And we use this property to melt hydrate blockage or to prevent hydrate formation. There are three main structures of hydrate. The initial or the common structure is cage, a small cage. So all of these different structures, they have a small cage. So 2 of these small cage and 6 of the large cage, this is structure 1. And then 16 of the small cages and 8 large cages form structure 2. And these cages, they are slightly different. This one has 14 faces, and this one has 16 faces. And then a structure H normally does not form in natural environment. So normally in oil industry, 99 or 95% of hydrate are structure 2. And very small, when we have very lean gases, we can form the structure 1. Now, there's a video showing the hydrate formation. This is a cell, high pressure cell, and you can see that at the interface, most of hydrates form at the interface. The reason they form at the interface because the amount of gas in hydrate structure is a lot more than the amount of gas in aqueous phase. Therefore, hydrate normally start at the interface. But for formation of hydrate, we don't need gas. Hydrate can form from gas dissolved in water. Here you don't see any gas molecule, but we can form hydrate. And you see that CO2 they have also formed hydrate with methane, but CO2 here you can see that is forming significant amount of hydrate in the aqueous phase without any gas phase. And we can control the rate of hydrate formation by playing with the pressure. And you can see that they are like a tree because they want to lose the heat. So remember, lose the heat, so they form sort of fins to lose the heat because hydrate formation is exothermic. it produces a lot of heat. So we need to use the heat. Now, as I mentioned to you earlier, different pure compounds have different tendency towards hydrate formation. In the gases we had in the industry, H2S, you see that it is very strong hydrate form. After that, IC4. After that, propane. After that, C2. After that, CO2. Yeah? And after that, methane. And then nitrogen. The point that changing the angle, this is the bubble point. Basically, vapor pressure line, and where above vapor pressure line we have liquid, below that we have gas. So that gives you a feeling that how the tendency of different compounds in forming hydrate. So if hydrocarbon is a mixture of these compounds, so depending on the composition and concentration, you can have hydrate phase boundary of the system somewhere in between. So for example, if it is here, then CO2 is an inhibitor, nitrogen is an inhibitor, but methane is a promoter. If it is here, then H2S is a promoter and methane is an inhibitor because they make it hydrate formation difficult. So the phase boundary of the system depends on the composition of the gas. And as I mentioned earlier, we have two major hydrate structures in the oil industry. Now, I just used our software and predicted the hydrate phase boundary of this mixture. I call it natural gas for future users of this mixture. So here I'm plotting the hydrate phase boundary for the structure 2 and the structure 1 using that gas this mixture. So its operating condition is here, then structure 2 only form. If it is here, then there is a potential for both structure 1 and structure 2 forming. So that's something that can be important when we are trying to prevent hydrate formation. So, it's better to be able to predict the position of different structure when we are trying to prevent hydrate formation. There is another mixture. This is a very lean gas nugget field in the North Sea. You see that 98% is methane, with a small amount of different compounds. You see that here, the structure 2 is to the left of the structure 1. So hydrate determining phase boundary structure is determined by structure 1. So here is that 5% I told you that the system is structure 1, and 95% of the system we see around the world are structure 2. This is another system, and this is from Middle East. Another system, this is the composition. Here you see that structure 1 and structure 2 are very close to each other. And at low pressure, structure 2 is stable, and high pressure, structure 1 is stable. The reason it's more stable because it can form first before the other structure forming. Now, condition that we can form a hydrate blockage or hydrate problem is high pressure, low temperature. When we have choke, regulator, vent, safety valve, safety valve open and then can form hydrate and blocking the safety valve itself. Water in the pipeline remaining from pressure testing or off-spec gases, they can all result in hydrate formation. There are many more cases, but just an example where you have to look for hydrate, where the risk of hydrate is maximum. So how we prevent hydrate formation? Here, as I mentioned to you, you can plot this line easily by knowing the gas composition and water composition. Then depending on your pipeline condition, most pipeline, they have basically continuous drop in pressure and temperature, and they can go inside hydrate phase boundary. But there are pipelines that can have a strange behavior. This is Ommelanga in Norway, that we have a continental shelf that drop the depths of water for around 1,000 meters. So at the bottom here, the temperature is -1, -2, so it's very cold. And then we produce here, and then the pipeline goes to the continental shelf, and then here the depth is a lot less, and the temperature will increase. So you see that here, the inlet from the well to the pipeline is outside hydrate phase boundary. But as we progress, it cools down and then can go inside hydrate phase boundary. And then it comes up, the temperature increases, but obviously pressure is dropping. And then here again, it goes outside. So you see that at the beginning and the end, we don't have hydrate formation, but in the middle somewhere here, we can have hydrate formation. Now, how to prevent hydrate problem? So one option is that hydrate, you can look at hydrate as a reaction, that you have water, you have gas, you form a solid. So if you remove one of the reactants, then we don't form hydrate. So for example, if the operating condition is 10 degrees and 200 bar here, we are inside hydrate phase boundary. But we can reduce the amount of water by dehydration unit and reduce the amount of water. For example, here we have 500 ppm water. Here we have 200 ppm, 150. We need to reduce the water content between 100 ppm to 150 ppm. So we can reduce the amount of water and prevent hydrate formation. But reducing the amount of water is basically expensive. You need facility, especially offshore, is not possible to have. But you can see that this is hydrate forming from water in the gas phase, because you see that homogeneous hydrate formation. So either hydrate forming from gas phase or the gas velocity, which is high velocity, form water into sort of mist. And that mist, water droplet, they basically do not form a liquid phase at the bottom of the pipeline. So hydrate is forming like this. Another important point these days that we are talking about carbon capture and storage is behavior of CO2 and hydrate in CO2 stream. So we have CO2, we want to transfer CO2 to somewhere offshore to inject it to the reservoir. This is phase behavior of CO2. You can see that the basically trigger point is -56.4, and the critical point is 31, and temperature and pressure is 73. You can see that the system can go within critical point, and as you know, predicting behavior of the system near critical point is not an easy task. So here is hydrate phase boundary of pure CO2 when we have extra water. If we have extra water, this is hydrate phase boundary, this is bubble point of CO2, the dashed line, and then here is above bubble point CO2 is liquid, here CO2 is vapor. So that's fine, that's similar to any other compound. But if you look at the amount of water, you can see the amount of water in hydrocarbon phase, and this is versus pressure. And look at the, for ethane, for example, here, the blue line, you can see that this is bubble point of ethane. You see that the amount of water in liquid ethane is less than vapor. Yeah, this is vapor. This is a bubble point of ethane at this temperature, 5 degrees. You see that this is vapor ethane, this is liquid ethane. You see that the amount of water dissolved in liquid ethane is reduced. And similarly for propane. But for CO2 and H2S, when they become liquid, the amount of water increases. When they become liquid, the amount of water increases. So the liquid CO2 can dissolve more water. So this is the amount of water in vapor and liquid CO2. This is at 15 degrees. You can see the bubble point of CO2 is around 50 bar. You can see that initially when you increase the pressure, you see the amount of water in equilibrium with vapor is dropping. But when you go, similar to any other compound, but when you go to the bubble point, you see that with increasing pressure, the amount of water increases. So when we have limited water, then it will be a problem. You see that when we have limited water, if we have plenty of water, this is phase envelope of CO2, as I showed in 2 figures earlier. But when we have 250 ppm water, then here up to bubble point is similar. But when we reach the bubble point, there is a competition between hydrate to form hydrate, get the water for hydrate formation, and liquid CO2. And here liquid CO2 wins because it can dissolve more water. So therefore you see that there is a discontinuity in the phase behavior of CO2 hydrate. So CO2 hydrate phase envelope would be something like this. Okay, so not a lot of software can predict that. So be careful the software you are using for liquid CO2. This is a real case. A company approached us and they said that they have this triangle operating condition, and they asked us if we have operating condition like this, is there any risk of hydrate formation? And if you plot it, then you see that no, because this is outside hydrate phase boundary for liquid CO2. You are above the bubble point of CO2, this blue line, the bubble point of CO2, and the above hydrate phase boundary is here, and this is outside hydrate phase boundary. So if we dry the CO2 to 250 ppm, then there is no risk of hydrate formation. And then they said, oh, we have 2% hydrogen. Will that change your story? When you have two compounds, then you have a phase envelope, and this is the phase envelope of CO2 plus 2% hydrogen. And you see one of these points will move to inside hydrate phase boundary. Now there are two options here. They have to dry further, or they have to use some inhibitor. So this has been published. It's been 123,778. So that was about dehydration. And then you had other option is that to increase the system temperature or heating or using.
Excuse me, Bahman. We have some comments from some audience that the quality of the voice is not so good. They have some problems with the voice quality. Is there anything that we can fix it?
Maybe I speak slower. I'm using a microphone.
Okay.
I think that's the best I can do.
Mm-hmm.
I can use computer microphone, inbuilt microphone.
Okay. Let's try with computer. Yes.
Okay. Me? Hello.
Hello.
Hello. Yeah, can you hear me?
Yes, maybe it's better.
Yeah, I'll try with computer. Yeah.
Okay.
Microphone.
Okay. Sorry.
No, it's fine. It's fine. So one option is to increase system temperature or use insulation, and the other one is reduce the system pressure. First, I'll discuss increasing temperature. Yes, if you maintain the pipeline temperature and or heat it, then we can move outside hydrate phase boundary. This is especially used in countries like Norway that they don't like to use inhibitor. They don't like to use they don't like to use any inhibitor because of environmental issues. So that's another option, but obviously it's a bit expensive. The other option is that to reduce the system pressure. We don't really do that because pressure is energy. We don't want to lose energy. If it is only 1 bar or 2 bar, move us outside hydrate phase boundary, that's fine because we can recover the pressure in the compressor unit and therefore the extra cost, but we really don't use pressure drop for avoiding hydrate. So we need to find another solution. We only use it for removing the blockage. Injection of thermodynamic inhibitor, methanol, ethanol, glycol, and other inhibitor, they basically work on the water phase. It's not as much dependent on the hydrocarbon phase. So what they do, they basically dissolve in water. So when they dissolve in water, then some water molecules are busy dissolving them. So we don't have enough water molecule to form hydrate. So we need to cool further. And that's the way they work for avoiding hydrate. So the problem with thermodynamic inhibitor is that we need a lot of them in the aqueous phase, between 30 to 50 or 60%. So if we have high water cut, that's going to be very expensive, especially offshore. So when you are using thermodynamic inhibitor, you need to be very careful about not forming salt block, because salt is soluble in water. It has a limit for solubility. For example, NaCl, you can dissolve 25% in HCl, but anymore, it can become soluble. But the alcohols are miscible. They can dissolve from 0 to 100% alcohol or glycol in water. So if they start competing with each other, what will come out is salt. So you need to be aware of, be careful when you are using hydrate inhibitor and salt. This is a picture from a wellbore in southern North Sea. Another option is to use antiagglutinant. Antiagglutinant, they don't prevent hydrate formation, but they allow hydrate to become a slurry and be transported. You can see that without chemical, with time, they become bigger and bigger. But with antiagglutinant, no. I have a video here, if I can show it. This is a testing antiagglutinant. You can see that the ball is here. This is hydrated slurry. And we need to make sure that the ball can move inside the slurry. And also show that if hydrate is sticking to the wall. But there are other techniques as well. That's one of the techniques for evaluating antiagglutinant. One point that I wanted to expand a little more on using a kinetic hydrate inhibitor, but I'm worried about the time. But kinetic hydrate inhibitor, they are believed that they can delay hydrate formation. They can delay hydrate formation for a certain period of time. And for example, here, you see that the system, this is temperature at 4 degrees. This is the cell pressure at 1400. You see that there is no, initially because temperature drop, pressure is dropping, and then pressure is constant up to 1400 minutes. From 200 to 1400, so 1200 delay in hydrate formation. So that is around 20 hours. So if the fluid moves outside hydrate phase boundary within 20 hours, it doesn't form it. But in reality, we investigated a bit more. We saw that without inhibitor, you see that hydrate forming, you cool down the system, you need some subcooling to form hydrate, and then follow the hydrate phase boundary of methane. This is methane. And then when you come out of the system, then it melts. When we go back and cool down again, now we have nucleation, so hydrates form easily, okay? So there is no, this is subcooling required to start nucleation, but when we have nucleation, there is no subcooling required. Now, we repeat this system, this test, with very small amount of PVCap. You can see that we form hydrate, yeah, but the rate of hydrate formation is slower. This is every 5 minutes. So when we want to melt hydrate, you see that we have to go a lot outside hydrate phase boundary. Then previous one, we just needed 1 degree outside and dissociate hydrate. Here we need around 3-4 degrees outside hydrate phase. So something is happening here. And once we go on the phase boundary, you expect this to go this way, but it goes this way. What does it mean? The hydrate is melting. So, and then if you cool down, you see that's formed here. And here, up to this area, it doesn't form. So we realize that kinetic PVCap based kinetic hydrate inhibitor, they have more than conventional kinetic hydrate inhibitor. So they basically work like a thermodynamic inhibitor. And remember, the amount of inhibitor is very little. So ideal for offshore rigs that we don't have enough space for storage. So we have done a lot more tests on it and find some region, we call continuous inhibition region, a slow growth region, and rapid growth region. So we identify this region, and also that we have a slow dissociation region, It means that if you have KHI, you have to be very careful not to form hydrate, because if you form hydrate, you need to heat a lot more. So just coming out of hydrate phase boundary is not enough. So we identified these regions, and from this region, this is for methane, then we tested different chemicals, and you see that different chemicals, they have different protection. Yeah, they have different protection. Some they have no protection in a structure 2, structure 1. So this will enable us to design or predict which KHI will work for which system. And that gives us huge ability or advantage, because in the past, KHI needed to be tested individually, but now we can choose which KHI. For example, if we are 6 degrees inside hydrate phase boundary, like here, we can use all inhibitor except F. If we are, for example, 8 degrees inside hydrate phase boundary, we can use C and B. So we can decide which inhibitor to go further testing. So we don't need to test all inhibitor. Now, how we do that? The first plot the stable structure. Here, for this natural gas, which was 85% methane and 5% ethane and propane and the rest, we structure 2 stable structure. And then structure 1, PVCap, we know that PVCap prevents the structure 2. So the strength of the chemical is from structure 1 onward. So for this chemical, for PVCap, we have the 5.2 degrees inside the structure 1. So total inhibition becomes 5.2 here and around 5-6 degrees, so 11 degrees. And we can also plot a slow growth region, and we can find out the fast formation region. So you see that we can, for this system, for the structure 2, KHI can provide 10 degree subcooling. But if you go for the other system, that structure 1 is stable, lean gas that I mentioned to you, nugget, you see that the structure 1 is stable, and the subcooling we can get is 5.2. This is another case from Middle East. You can see that here at low pressure, structure 2 is stable, at high pressure, structure 1 is stable. But the inhibition we can get is only 5.2. So this will enable us to predict if the KHI will work in the system or not. Obviously, in the course, we can discuss this about a little bit more. Now, I want to divert your attention to somewhere else. Now I want to move some of the new technology in preventing hydrate formation and blockage. If you remember, I said that hydrate formation depends on hydrocarbon phase and water phase, aqueous phase. Now, if we have these two, we can predict hydrate phase boundary. The other point is that, can we predict this one? Yes, we can, by using computer simulation or some pressure and temperature sensors, so we know what is the condition of the pipeline, and then we can adjust the amount of inhibitor we inject to move this curve back and forth, okay? But to be able to do that, we need composition of hydrocarbon phase, and we need a composition of water phase. Composition of hydrocarbon phase within a short period of time doesn't change. Basically, it doesn't change. So hydrocarbon phase doesn't change. The only change that will change is the composition of aqueous phase. And if we find something that can detect or determine composition of aqueous phase, we can plot this hydrate phase boundary and safety margin. And it is very good to be able to do that, because we have uncertainty on the water cut, and then if equipment malfunction or human error or changes in the system condition, or if the inhibitor is off a spec. So here we have a device here, we call it HydraCHEK. Basically, you can have a 100 cc of the produced water. You measure electrical conductivity and speed of sound. From that, you can, like two equations, two unknowns, the system will determine the concentration of salt and inhibitor. And then you have hydrocarbon phase, you have water phase, and then you can use a correlation or model and predict hydrate phase boundary. If the predicted hydrate phase boundary is here, then there is a risk of hydrate. You need to increase the amount of inhibitor. If it is here, it is very close. If you can put a safety margin, then 2 to 3 degrees safety margin. And then finally here, we have too much inhibitor. We have too much inhibitor. So that traffic light I mentioned, it is achieved here. The other novel idea or new development is using this property of different components in forming hydrate. So if hydrate form, this compound like IC4 and propane or H2S will be trapped in the hydrate structure. So therefore, the concentration of this compound in the gas phase is reduced. By that, we can basically get early warning that hydrate is forming in the pipeline. And then we can also, for example, if you have a blockage, by analyzing the gas, we can say is the blockage being removed or not. Or also, we can also predict the position or the point of hydrate formation. The last slide, depressurize the different option for blockage. The popular one is depressurizing. Use heating, injection of thermodynamic inhibitor. We can change the composition of gas on combination of the above. So at the end, hydrate is not bad news. This is hydrate can produce gas energy. Water can be from here. Yeah, and we will be prepared for National Geographic. So thank you very much. Any question?